Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle LeetCode problem 1091, shortest path in a binary matrix. After that, we'll go over two actual variants of the original question that Meta asks. These types of problems are a mixed bag of BFS and DFS, so I have no doubt it'll be very, very fun. Okay, let's zoom through the problem description. We're given an n by n binary matrix, so taking a look at our visual here, it's a 2D integer array that only has zeros and ones. We want to return the shortest clear path, in which a clear path is defined as a path of only zeros that must start at the top left cell and end in the bottom right cell. Let's take a look at some examples. Again, a clear path is required to begin at row 0 and column 0 right here, all the way to the bottom right cell at the last row and the last column. And for reference, here is another one. Observe that we can traverse in 8 different directions. This includes diagonals. Our task is to find which one is the shortest path from point A to point B and return the minimum number of steps it took. I'll spoil the answer for you right now. The shortest path we took was this one. Counting it, it took 1, 2, 3, 4, and lastly 5 steps. Therefore, the integer 5 is our answer, and that's what we return. That seems easy, but how do we mash together for loops and if statements on random data structures to come to a programmatic solution? Let's do some discovery work. Take a look at our grid here. Once again, our goal is to figure out the minimum number of steps to go from the top left cell all the way to the bottom right cell. If you're a nerd with photographic memory, you'll recall from geometry class that in a right triangle, in which these are the two sides right here, that the hypotenuse is the shortest path between two cells, and thus represents the minimum number of steps. It's the 1, 2, 3, and then 4. But can we always go diagonally? What if there were obstacles in the way? This means we'd have no choice but to go around. Now the problem becomes a bit trickier. Let's take a deep breath, note down each and every possible path, and then maybe the solution will naturally come to us. Okay, so we must start at the top left cell. That technically takes us one step to get here. From here, where are all the possible cells we can traverse to? Well, that would be this one, and this one. To each of these cells, it would take an additional step from where we came from, so we can simply increment our step of 1 here to get 2. Let's note that down. Makes sense so far. We're not sure which one leads to the shortest path just yet, but let's continue this train of thought. On what I consider the next level of cells, where can we traverse to next? Let's inspect each cell one by one. For this cell, let's go over the 8 possible directions. Can we go up? Nope, that's out of bounds. Can we go top right? Still out of bounds. What about the right? Yes, it's a clear cell of integer 0. Going here takes another step, so what's 2 plus 1? It's 3. Up next, can we go to the bottom right? We can't because there's an obstacle there, denoted by the 1. Can we go to the bottom? We technically can, but that would take 2 plus 1 of 3 steps, not the previously established 2 steps. The path of 2 is obviously shorter than the 3, so we'll retain the 2. No need to revisit a cell in these cases. Same deal here, same deal here. Because if we go to a neighbor just to go back, which would cost us 3 steps, 3 is definitely not preferred over the 1. And lastly, the top left cell is also out of bounds. We don't want any out of bound errors. Okay, wow, just for one cell, that was very time consuming. Don't worry though, I'll only really show this once in this demo. The next cell to be considered would be this one. Where can we go? Well, all of these are visited, so we opt not to. These are obstacles, so we can only go to these 2 cells. Going to this one would take another step for a total of 3 steps, same here. After that, we'll consider this one where we quickly conclude we can't go anywhere, so we do nothing. On the next level, let's see what neighboring cells we can move to. At this cell, can we go to the left? Nope, because a path of 4, the 3 plus 1, is not favored over our established shorter path of 2 steps. Okay, we've seen it enough times now to confidently say that when we already visited a cell, there's no need to revisit it. That specifically, the first time we ever get to a cell, that is the shortest path to get there. And the minimum number of steps written is indeed the minimum number of steps. It's not too far-fetched of an inference that when we get to the bottom right cell and determine the minimum number of steps, that would be our answer. Okay, cool. Where were we? We're about to process the new level of cells. Let's do it slightly quicker. From here, where can we go? It's only these 2 cells. It would take a total of 4 steps for each of them. Up next, for this cell, we know we can go to these 3 clear cells, each with also a total of 4 steps. Examining our last cell of this level, there's nowhere else we can go. We could go down, for example, but 3 plus 1 of 4 would make no difference of the already established shortest path of 4. Okay, on this next level of 4s, where can we go to? Well, for these, we easily observe there's nowhere to go. But for this cell, you can easily go down, which takes 5 steps. And then for this one, you can go to its right, also 5 steps. Amazingly, we reached point B, the bottom right cell. We're done. We've covered all the possible paths and the minimum number of steps to get there. This is our answer. This is what we return. Visually, this is what the shortest path was. Hopefully that sets up enough context for us to realize that our algorithm of choice should be the level order traversal algorithm. I hinted at it throughout the example, but this was our first level, second level, third level, fourth level, it's kind of awkward, and lastly, the 5th level. I won't bore you with a 10-minute explanation of level order traversal since it's out of scope for this video, but let's redo this whole example real quick, but with one level of abstraction closer to the code. Check out our queue here. We named it Q for short because we're smartasses. As for the first thing we do in level order traversal, it instructs us to seed our queue with a starting cell that can be identified by a row of 0 and a column of 0. Let's write that down. Recall that as per the requirements, it takes 1 step to get here. We'll need this integer field in our queue data structure as we go level by level. That's how we'll know when we get to the last level that 5 is our answer. There's nothing stopping us from including it in our queue, so let's do so. And just so you know, this object in our queue will be organized into a class called cell that will have 3 fields, 1, the row, 2, column, and finally the number of steps. Alright, from here we'll enter a while loop that, so long as our queue is not empty, will keep processing cells. Okay, so up first we have this cell right here at row 0 and column 0. Remember, we have an overwhelming 8 possible directions to traverse to, but among other error cases, we cannot access out-of-bound cells. That much is obvious. Inversely, the leftover cells are clear cells because they have an integer of 0, so let's jump to them. Doing so means pushing all of them into our queue. So we have our first cell, second one, and last one at 1, 1. But what about the steps? The other field in our state object here. Recall we add 1 from where we were, that's 1 plus 1, that gives us 2. We'll also push that into our queue. And visually, let's denote the 2 steps, just to make it easier to follow along. We've processed our first cell. We have no more uses for it. We'll pop it from our queue. For what I consider the next level of our level order traversal, let's repeat our logic. Which cell is up first? It's the one at row 0 and column 1. Right here. We'll try to see if we can traverse in all 8 directions. Let's try them out. We'd get an out-of-bounds error if we go top left, top, or top right. So we won't even try. What about the right cell? Sure thing, it's a clear cell. Let's enqueue this cell with a row of 0 and column 2 with the number of steps it took to get here. From where we were, that's the 2 plus 1 to get 3. Reflecting that in our queue, it's row 0 and column 2 with 3 steps. Moving on, can we go to the bottom right cell? No, because 1 tells us there's an obstacle there. Lastly, what about these 3 cells? What did we say about already visited cells? The moment we get to a cell is the shortest length to get there. So we'll bite our tongue and refrain from traversing to already processed cells. Let's think about the code though. How do we know a cell has already been visited? Take this one, the first cell. These step numbers are purely visual. They only manifest a concrete form in our queue data structure right here. That means we'll unfortunately revisit this cell and overwrite it with the wrong number of cells, and even worse, we'd be stuck in an infinite loop, going back between the two, inaccurately incrementing the number of steps for all eternity. Thus, here's what we'll do to prevent this. Rewinding a bit, when we seeded our queue with the first cell, we'll cleverly manually overwrite the value of 0, which denotes a clear cell, with a 1. Recall that 1 represents an obstacle. This sets us up for success when at this cell, the one we're currently examining, look at the left neighbor, we know not to traverse there. Setting the first cell to 1 was a hard-coded line of code, but how do we programmatically set all of the other cells as visited? Let's identify an opportunity in our BFS algorithm. When we discovered the first cell's clear neighbors, which were these, yes, we'll enqueue them into our queue, but we'll also mark them as visited with an integer of 1. Okay, that handles all the possible error cases. This brings us back to present day, where we were processing this cell. It's obvious now that we cannot traverse to these 3 neighbors. The only cell we could go to was this one. Let's also mark it as visited. Finally, we're done with this cell, so let's pop it from our queue. The next cell to process is the one at row 1 and column 0. That's right here. I'll tell you right now, going over the 8 possible directions, these 3 are out of bounds, these 3 are already visited. That leaves just these 2. Let's add them to our queue. The order doesn't matter. I'll add this one first, and then the one below it, both of which took an additional step from 2 to get 3. Remember our new piece of logic? Whenever we enqueue neighboring cells, we'll also mark them as visited. So let's do so, and visually reflect the minimum number of steps it took to get there. Amazing, we're done with this cell. Let's pop it from our queue and move on. We have this one up next, which is right here. It's quite obvious we can't go anywhere, so we do nothing, add nothing, and we'll pop it from our queue. And with that, we're now on the next level in our BFS of the 3-steppers. I can already tell this is going to be extremely redundant. I have the attention span of a goldfish, so allow me to speedrun the rest of this example. Okay, wow, we are so fast and efficient. We're now processing the very last cell, which happens to be the bottom right one. We know for a fact that it took a minimum of 5 steps to get here. That is our answer. Therefore, we'll sneak in an if statement that on any given cell, if we're at the last row of 3 and the last column of 3, in this example at least, then we'll immediately return the steps field of the 5. Remember, we can access this variable in our queue. But yes, this is our answer. This is what we return. And if you're curious what the shortest path we took was, it's this one right here. We really destroyed this example. It's the most unreadable thing I've ever seen in my life, but I'm about to add even more fluff to this diagram. There are 2 annoying edge cases we have to think about. What if the top left cell had an obstacle to begin with, or the bottom right one for that matter? In either case, a path is not possible. The problem description will just require us to return -1. That would be our answer. Aside from that, what is our time complexity? Well, since we're given an n by n matrix, and we process each one once, then that will give us a time complexity of n squared. The space complexity would be our queue, which is n. In other words, the most cell that our queue would have would be the longest diagonal possible. It can be generalized to just n. Okay, let's take a look at the code. The edge case I just mentioned is still in my goldfish brain, so let's handle that first. That if the top left cell is an obstacle or the bottom right cell is an obstacle, then we'll return -1 as instructed. Now, before we start our level order traversal, let's prepare some abstractions and useful data structures. First, we need to define our cell object, which will represent the state of our queue. Remember, it has 3 fields: the row, the column, and lastly, the minimum number of steps that it took to get to this row and column. Secondly, we can traverse in all 8 directions, remember? For us, we'll choose to use row and column offsets. We'll call it directions. I really don't want to type it out, so allow me to copy and paste. Okay, so we're finally ready for our big day. Let's implement level order traversal. Remember, we'll manually set the top left cell as visited by overriding it with a 1. Next, we'll create our queue of cells, call queue, and seed it with the top left one. Recall it has an initial step of 1. We'll keep looping so long as our queue is not empty. On each iteration, we'll reference the cell's row, column, and number of steps. And since this is all we need references to process the current cell, let's pop it from our queue. Now let's add our one and only base case if we reach the bottom right cell, which can be found at the last row and the last column. Then we can just return the number of steps. Otherwise, we'll loop in all 8 directions, using D for directions, since we're rebels, and refuse to use the conventional I pointer. For each direction that we're on, let's write some syntactic sugar. We'll add to our current row the current direction we're on, specifically the row offset at the 0th index. This gets us the new row. We'll do the same thing with the new column, adding to column the directions offset accessed at the 1st index. Okay, with this, let's inspect a bunch of error cases in a systematic way. Is the new row out of bounds, aka it's negative or goes beyond our matrix? If so, we'll simply continue and try the next direction. Next up, is the new column out of bounds? In other words, it's negative or, similarly, stretches beyond the last column. Likewise, we'll just continue and move on. After this, we must be in bounds, but is this neighboring cell already visited or originally an obstacle? Either way, it'd be denoted by a 1, we'd also continue. Otherwise, if we make it past the gauntlet of if statements alive, we'll mark the new cell at the new row and new column as visited. Not only that, we'll push its coordinates of the new row and new column, as well as the number of steps plus 1. Believe it or not, that's the whole algorithm. There's just one thing left to do, which is to return -1 at the very end, because our compiler would be threatening us with red squiggles. But we know in our hearts that this line is unreachable. Very cool. We have a lot of variants to get to, so let's start on the first one. The variant packs on another layer of requirements to the original LeetCode problem, where we still want the shortest path in a binary matrix, but now we want to return the actual path itself, no longer the minimum number of steps. Other than that, nothing else changes. So for our example here, I'll spoil it for you right now. This is the shortest path from point A to point B, in which the first cell we visited was at row 0 and column 0. Let's note that down in our path, 0, 0. Up next, we have 0, 1, so let's write that down. 1, 1, and then lastly, 2, 2. This is our answer. This is what we return. To solve this variant, it's quite relieving to hear that we only need to add a few lines of code to our OG implementation. And since I've already gone over all the intuition, explanation, and walkthrough, I'll narrow in on the spicy parts of this variant with this same example. Let's take a look. Alright, taking a gander, we conveniently note that our queue has already been seeded with the top left cell with a step of 1. But wait 1 second, we don't need to return the minimum number of steps anymore, right? Furthermore, we had established from the previous problem that the first time we visit a clear cell, any one of these, is the shortest path to get there already. Thankfully, our level order BFS will still do its magic to reach the bottom right cell in the fastest way possible. Furthermore, we only care about the path of cells. Therefore, I announce the steps field in our cell class useless, so let's remove it. We now want to track the current path of any given cell. Nothing stopping us developers from stuffing our cell object with a path field. That starts at 0, 0. Okay, we have enough context in our cerebrum to begin this walkthrough here. Before we start our while loop, let's make sure we manually mark the top left cell as visited. Okay, now we can begin. Let's look at all of the first cell's neighbors. Where can we traverse? Not the ones that are out of bounds, we'll skip those. Not the ones that have obstacles, we'll skip those too. That just leaves one clear cell to its right. We'll do the same thing as before and queue it into our data structure, row of 0, column of 1, and remember, we'll mark it as visited too. But wait, what about its path? Well, we know we came from 0, 0, so let's copy that and then tack on, where we currently are, the new row of 0 and column of 1. It's the 0 and then 1. Amazing. We're done with this first cell, so let's pop it from our queue and move on to the next one. Where can we go to? I'll spare you redundancy. We can go to the right and then bottom right. As per usual, we'll add both into our queue data structure of 0, 2 with a path from 0, 0 and 0, 1. Let's copy that and then tack on the new row and new column 0, 2. Let's mark it as visited and add this one as well. Row of 1, column of 2. For the path, let's copy where we were. That's going to be the 0, 0, 0, 1, which is right here, and then not before visiting the new row, new column 1, 2. So let's add that 1, 2. Don't forget, we'll mark it as visited. And now we're done with this cell. Let's pop it. Moving on, what's the next cell? It's this one right here. But as you can see, there's nowhere we can go, so we do nothing. Let's pop it from our queue. Moving on to the next one. Obviously, there's only one place we can go. It's the neighbor right below it. Let's add it to our queue. 2, 2. Where did we come from? It was these 3 coordinates. To verify it, it's the 0, 0, 0, 1, 1, 2, and then now the 2, 2. So more formally, it's the copy of where we were with the new row and column tacked on. Very interesting. Let's mark it as visited. And then let's pop this cell. Now we're on the very last one. We can happily stop here because we're at the last row and the last column. The path that we ultimately took can be accessed right here. And visually, that would be this path. This is what we return. This is our answer. As for our time complexity, you'd think it's n squared, but it's actually n cubed. How, you ask? Well, we process every single cell, which n by n gives us n squared. But on each iteration that we process a cell, we also copy the path. This is generalized to a big O of n operation. That times the n squared ultimately lands us at n cubed. This is very tricky, and your interviewer will be salivating at the thought of you messing up. So make sure you get it right. The space complexity is n squared because the worst case level, if they were all zeros, would be this diagonal. And if each of those contained the path, a big O n, it would come out to be n squared. All right, let's move onwards to the implementation and modify what needs to be changed. First up, let's modify our cell schema. We no longer care about the number of steps. We'd rather have the path, which is a nested list of coordinates. In our function, if we encounter an edge case where the top left and or bottom right cells are obstacles, we'll return an empty vector instead. And while we're at it, let's also return empty vector at the end of our function. Again, we just want our compiler off our backs. Now, the first thing that needs to change is this line when we seed our queue. We'll now want a starting path of 0, 0. Makes sense? In our while loop, we extract the row column, but no longer the number of steps, it's the path instead. which means our terminal case here will also now return the path, which is exactly what we want. The last thing we need to change is to actually copy the path, which is normally trivial, but I'm a C++ user, I don't know why, I didn't choose it, it chose me kind of thing. Since the friend function API returns a reference to the path, we don't want to mutate this state. So we'll just make a copy of it, let's call it path copy, and then thereafter, push into that copy of the new row and new column. This is indeed the new path, so instead of the steps +1, we'll enqueue the path copy. And that's it. If you're going to go through your code line by line to your interviewer, may I suggest a small matrix? Otherwise, it'd eat up a lot of your precious time. Anywho, let's jump into the last variant. Welcome to the last variant, where there's literally a 2-word change in our problem description. We want to return a singular path from the top left cell to the bottom right cell. I excluded a keyword in that sentence, but to call it out, we no longer care about the shortest path. Take LeetCode's example here. We could return this path or this path, it doesn't matter. Whichever one is fine, as long as we return one of them. We ask ourselves, does this requirement change anything? Can we still reuse our BFS implementation from before? Well, we absolutely can. It's completely functional, but in general, the interviewer is looking for a DFS solution instead. Allow me to reason why a DFS solution may be more performant than its counterpart. Let's take a look at an example. Yes, I know this is a graph, not a matrix, but algorithms like BFS and DFS operate the same on both data structures, or at least very similarly. Let's tritely call the root node the top left cell, or in other words, point A, and say this leaf node as the bottom right cell. That will be our destination. We want to go from point A to point B. I'm sort of pigeonholing myself into a very contrived example, but I'm trying to get you to pass the interview. What if we are given such a graph with a high branching factor, meaning each cell can have potentially many children? The implications this has on our space complexity should not be underestimated. If we ran a BFS, at one point our queue would have this whole level stored. That's a grand total of 10 nodes. But what if we ran a DFS? Well, there's a chance that we take this path and thus only accrue 4 stack frames. 4 means it took up less space than the 10, so DFS wins in this battle. Moreover, DFS never cared about the shortest path, only a single path, whether it was this one or if there was an edge going to this node, then this would have been an option as well. This brings up to our next point. DFS can beat BFS in terms of time complexity, in the case that the bottom right cell node that we're trying to get to is deeper down and not super wide. Say this one right here. This will be our new point B, no longer this one. With BFS, we'd have to process this level of 1 node, the next level of 3 nodes, and then all of these nodes, all 10, before we can finally process our bottom right node. With DFS, if we took this route, we'd only process 3 nodes. If we look at them side by side, 3 nodes versus the grand total of 14, DFS wins again. To expound on this, we care about the deeper path, not the shortest one. I will say though that the big O of both space and time complexity doesn't really change. But in practice, knowing when to choose one over the other can really boost performance given certain graph layouts. In this very specific example, and most likely the one that your interviewer will give you, DFS is the clear winner. For our code implementation, we'll intentionally choose to start our code using the OG problems code as the base template. And essentially all we'll do is convert our previous BFS solution to a DFS one. Let's get started. Alright, so before I forget, let's change these -1s to empty vectors. 1 there, and 1 on line 38. Remember, we're trying to go for DFS, therefore we don't need a queue, and therefore this cell class. We can get rid of that. Let's now create a helper DFS function. Let's call it DFS. It'll take in a number of parameters, the input matrix, of course, let's call it grid, our current path, which is also a nested vector, as well as the current row and column. We'll decide to return a Boolean to short circuit our DFS the moment we find the desired bottom right cell. Let's do a very error-prone thing and copy and paste the body of our BFS into our DFS function and change the code appropriately. For once, we no longer need a queue data structure, so let's remove all traces of it. That includes this while loop as well as any API calls we called on it. Okay, first order of business in our DFS. On any given cell, we'll mark its location as visited, which now will depend on where we currently are at row and column. The other thing we'll do is add the current row and current column as a part of our current path. Next, if we reach our base case, we'll return true to signify that on the backtrack, we've found the bottom right cell. No need to keep adding on to the path. After that, as per usual, we'll loop through all 8 directions, look at a neighboring cell at these coordinates, and see if it's out of bounds, or if it's already been visited, or it's an obstacle. If it's none of these things, we'll recurse to that clear neighbor, passing in the grid, path, but also the new row and new column. Now remember, if we hit our base case and return true, why keep recursing to other neighboring nodes? We'd rather carry back this true by returning it upstream. This saves us processing computation and memory. Now on the backtrack from any given cell, we've hit a dead end. That means the cell we're on is not a part of the resulting path. Let's pop it. And then return false. One last thing, let's initialize our path and actually call our DFS function. It is called DFS. We pass in the grid, path, a starting coordinate of 0, 0 as the top left cell. It was a good idea to hedge our bets and return an empty vector since our code was previously unreachable, but now with DFS that's no longer the case. Let's return the path instead. Awesome, that is it. Thanks for sticking it out, and I hope you learned a thing or two. I wish you luck on your interviews. And if you learned something today, please make sure you like, comment, and subscribe. Thanks for watching.